I'm Costantino Menna. I'm from the Department of Structures for Engineering and Architecture of the University of Naples. I'm also convener of the FI Betas group working on structures made by digital fabrication. All the presentation looks very, very interesting for the field of study I'm involved in, and actually I'm going to give you a different perspective, in particular from the structural engineering point of view, in particular working on structural elements. So I will give you a couple of examples of two beams concept that we have developed here in Naples, and I'll try to point out which are the limits and also the challenges that are still open to fully deploy these new technologies. Well, as I said, from the structural engineering point of view, digital fabrication with concrete has introduced a lot of opportunities, but at the same time, new challenges. So, first of all, we have the three pillars of traditional quality control methodology that are true for conventionally cast concrete are now affected and needs to be adapted to the different technologies of digital fabrications. We have that structural design must be updated, especially from a seismic point of view, but in general, a structural point of view. The same for materials. We have seen that these kind of materials are very different from conventional ones, and all the quality controls must be updated to guarantee the maximum performances and reliability of the same materials, and also the processes. In terms of structural engineering, one of the most critical aspect for sure is reinforcement. Many of the audience have asked about reinforcement because in different areas, but also referring to the structural typology of the element, we must know how to address this issue. The situation now is that moving from the conventional reinforcing bars that are used in cast concrete, the digital fabrication has introduced different options for reinforcement. First of all, the new reinforcement types affects the structural principle of the element. For instance, we can get ductile printing materials in which in the printable mortar we introduce fibers, structural fibers. Or we can consider different techniques to introduce external or passive reinforcement inside filaments or inside any printable mortars that we consider into the technology. And other options, for instance, could be avoid completely the reinforcement, as probably has shown the former presenter, or combining the solutions. These types of structural principle obtained with digital fabrication can be also related to the time, so to the stage of the process in which the reinforcement is added. And of course, the most interesting solution for adding reinforcement is when the reinforcement is added at the same time of the printing process. A recent review paper by Harold Croft has collected all the typologies and has classified these typologies in which the additive manufacturing is combined with reinforcing methods. We can see that reinforcement can be really different from changing from the different technologies available. For instance, in the layered extrusion technology that we have seen also from the former presenters, the reinforcement types can consist in rods that are placed in a parallel, orthogonal, or inclined way with respect to the printing layers. But also the reinforcement may consist of filaments woven around the concrete filament, or it can be inserted as a discrete fibers between the layers. Another types of reinforcement is when the steel represents a support for pouring or for spraying concrete around the steel cage, or as the last example, a simultaneous use of reinforcement and mortar, considering the support types of steel. Well, by adopting these methods, we have already some structural objects that were printed so far. For instance, we have the 3D printed concrete pedestrian bridge developed and printed in the Netherlands, in which each concrete segment contains a structural steel filament, and then the bridge is conceived as a post-tensioned bridge. Or we have many examples of the smart dynamic casting, in which the structural steel is used as a support, and then the concrete is cast step by step throughout the height of the column. Or in the mesh mold process, for which the concrete is poured inside a steel mesh that represents also the reinforcing system for the structural element. Well, when we introduce the steel inside a structural element with these innovative technologies, we have two types of problems. First of all, we can consider a new type of reinforcement, completely new with respect to the conventional ones. For instance, when we add filament inside the concrete layer, or we can try to adopt the conventional steel reinforcement in the form of bars inside a new digital fabrication technique. For instance, here on the right-hand side, you see some steel rebars, which are included between the layers of an extrusion layer technology to understand what is the effect of this combination. In both cases, we must say that what changes is that the failure modes will be completely different from the failure modes that we normally adopt in the design process. Okay, as well as here we see the bond is different due to the formation of voids, and as a consequence, during the design we cannot adopt the previous and available models for bonding between concrete and steel. So this is a key point for developing and for deploying this technology, especially when we deal, especially with reinforcing systems. I'm going to present here two examples. We're trying to show you how this critical point of reinforcement can affect the design of the structural elements. And these two examples consist of two structural beams, obtained by means of two different methods. In the first methods, we consider that the reinforcement is applied as an external reinforcing system, and in such a way this reinforcing method is innovative because different from conventional one. And I will show you how this innovation brings a real complexity for code compliance. The potential benefit is that for this external reinforcement technique, we can achieve a reduction of the amount of concrete when we produce this structural element. The second example is the other way around. So we adopt a digital fabrication technology to produce a lost formwork with concrete, and we adopt conventional steel rebar systems, and also the amount of steel is designed and quantified according to the structural code. So in this case, we start with a code compliance of the steel. And the benefit is that with this technique, we can achieve additional functionalities of the structural elements. But the examples I'm going to show you are manufactured at the digital construction labs in Naples, which I'm working, and it is still active to study particularly the structural aspects of digital fabrication. Well, the first example starts from a beam with a variable cross-section on the left-hand side. In particular, we have potentially a beam that changes the cross-section through the x-axis. And to apply these 3D printing techniques to the structural element, we ideally cut the entire beam into several segments, mostly depending on the dimensional capability of the 3D printing machine. Once the concrete segments are printed separately, we can merge together the segments with an external reinforcement systems, which is connected through an out-of-plane system of rebars. Of course, this is one of the possibilities, because all the segments could be also connected with post-tensioning cables. It should be noted that with these techniques, we consider the segments which are printed and are connected in the direction which is parallel to the printing directions. What is the benefit? The benefit is that each of the concrete segment can be optimized with respect to the mechanical properties. For instance, in the case of simple bending, each of the concrete segment can be optimized with respect to the bending resistant model. And in our case, we have chosen a strut and tie model which mimic the bending resistant model. Here is the result. So the 3 meter long beam is ideally divided into 5 concrete segments, in which you can see the concrete strut of the resisting mechanism, and then afterwards an external steel reinforcement system is applied. The steel reinforcement consists of longitudinal bars to guarantee the resisting bending moment, but also of inclined rebars for shear resisting mechanisms. These rebars are connected by means of hexagonal nut pipes and also male threaded steel elements, in order to calibrate also the tension inside each of the structure of the steel elements. Once printed, this beam has been tested, because there were no idea of the designed bending moment and the real capacity of the beam. And we have tested here in the lab in Naples to see if there are new failures mechanisms that are unexpected from the conventional design point of view. And we have to say that, of course, these appeared. So in particular, here you can see the flexural load versus deflection curve that highlights several drops into this trend. Because actually, during the loading phase, we experienced many cracks at the interfaces of the concrete segments, because most of the stress concentration was located into the points in which the external steel reinforcement was anchored. So many criticalities arose in terms of anchorage systems. In terms of positive outcomes of this reinforcing and this beam concept, is that if we look at the beginning to the initial flexural stiffness, by reducing a weight of more than 50%, before the first cracking, the flexural stiffness was intermediate compared to a full solid beam and the cracked solid beam. So as a starting point, this was not so bad. But of course, the local failure mechanisms at the interface was actually introducing a critical point that avoided the attainment of the yielding of the external steel. So we have a premature failure due to the anchorage failure. We have adopted the same techniques also to other beam systems, in particular to show the potentiality of this approach when we have different profiles of the beam, and we have applied this approach to the profile of the Vesuvius volcano, in which we defined at the beginning the upper and lower edge of the beam, and then we, by simulation, defined all the geometrical dimensions and the dimension of the external steel reinforcement to guarantee the resisting bending moment and also the minimum deflection, and this was the result. what we have learned beside the consideration that I made. So that first of all, many of the interfaces should be avoided, and this can be achievable by changing the printing path and employing a larger robotic system. And then another important consideration is that by loading the specimen into the direction which is parallel to the printing direction may be a problem for the compression load, because probably that direction is not the most not the stronger direction when we consider the anisotropy of the printed material. The second example that I'm going to show you is the lost formwork approach. In this approach, we use always, so in the lost formwork approach, we print the formwork, and in particular, we optimize the shape with respect to the new functionality of the beam for accommodating new systems, but also for guaranteeing that the minimum reinforcement and the amount of concrete is compatible with code compliance, in particular with respect to bending and shear steel reinforcement. This is normally done in practice with steel beams. So we explored the idea to consider concrete beam. The shape optimization with respect to minimum reinforcement and functionality has been made by means of finite elements. And here from the picture, you can see some of these stages. From these stages, we have to guarantee the stability of the printing layers, but also the interconnections between the shapes in order to guarantee a monolithic poured spaceman after we consider the formwork. Here, after showing this manufacturing part, also in the case of lost formworks, the local failure mechanism can limitate this technology, and this is what I'm going to tell you in the conclusions, because these two possible approaches for structural element production are feasible, but as far as we know at the moment, we have to improve our knowledge with respect to the failure mechanisms in order to drive and consider a much more reliable approach for the design. This can be done with a multidisciplinary approach, and also by considering some exceptions of the structural code in reference to innovative construction products, such as some annexes of the Eurocode 1990, that allows for experimental-based acceptance of the structural element. So, sorry for my final rush, and I'd like to thank you just for let the audience to ask some questions. So I was on time. Thank you.